All right, thanks for joining everyone. We'll give it just a couple of minutes here, just until noon, and then we'll go ahead and get started. I know people are still trickling in, but thanks for joining and looking forward to chatting about part costs and throughput. All right, coming up on the top of the hour here, and we have a lot to get through, so I'm sure people will continue to trickle in, but we'll go ahead and get started. Thanks for joining, everyone. This is a quick 30-minute webinar here where we're going to be talking about understanding part costs and throughput with Mantle. My name is Ethan Wright. I'm the Director of Marketing here at Mantle. If you've been on some of our webinars, you probably know who I am. We're lucky to be joined by Prescott, who will introduce himself in a couple of minutes here. Just some quick housekeeping before we get started. If you want to jump to the next slide here. Yeah, the Q&A, of course, feel free to ask any questions you have in the bottom in the Q&A. I'll actually be looking at that live, and we can always interject and ask Prescott questions throughout. Happy to answer anything as they come up, so feel free to use that Q&A. And of course, this presentation is being recorded, so you'll receive a copy of the slides as well as actual recording, the video as well. So if you have to drop off early or miss anything, do not worry, we'll get that recording over to you. Quick agenda for today, I believe. We're going to start with a quick just introduction of ourselves. We're going to kind of split this into two sections here, which the first is walking through really understanding part cost, look at a couple of examples of printed tools with our technology, understand what does it cost, how long does it take, and what are the kind of the drivers and the different things that go into the cost of a part that's printed with Mantle's technology. We'll then look at design specifically and understand what are the levers we do have that are going to impact this, and how can we optimize our designs to be the most efficient in terms of cost and print times. At the end, we'll go ahead and take some questions and answers, but we're looking forward to this, and thanks for joining. You probably know me if you've joined any of our webinars in the past. I'm Ethan, Director of Marketing here at Mantle. I have a background in engineering and product design, and always looking forward to educating people on new technologies and some of the successes we're having. But the real star here today is Prescott, who's joining us, who I was managed to convince to join us today. I'll let Prescott introduce himself, and he's really going to take it from here.
Yeah, thanks, Ethan. Excited to be here. Excited to present on the number of topics we have for you. I lead Mantle's customer success and application engineering focus. Our charter is customer support, service, enablement, growth. So a pretty broad charter, but this is certainly in our wheelhouse. So excited to provide some education here, some insights into how we think about part throughput, part cost. And to that point, I wanted to start by grounding this discussion in what Mantle has done to characterize part cost. We've developed a very comprehensive model, which is a tool we use during sales, during consultation with current customers. So I wanted to present on the various inputs that inform piece cost here, starting with a great example of a good fit for Mantle. This part, it's produced in our H13 tool steel. It's about 4" by 3" by 1" tall. It's a good fit. The reason I say that is because it has a lot of ribs in the center of that part, which would otherwise need some sinker EDM work to produce. This build, when run one part at a time, will take 55 hours to print on our printer, and likewise, there's a secondary sintering step, which will run in our furnace over a 42-hour period. This part consumes 614 milliliters of paste, and a couple of key assumptions we make for our cost modeling. First, we start with the amortization of our equipment. consulting with customers and folks internally alike, we have landed on a 7-year amortization schedule, which is pretty common. That's the depreciation of the equipment over time. Likewise, we model a 75% utilization rate. In practice, we see some customers are higher, some customers are lower. But what 75% utilization equates to is just shy of 6,600 usable hours on the printer per year. So what does this part cost to produce? All in, it's just a hair over $1,300. I'm not going to stop here. We're going to go through each of these inputs, each of these contributions to show just how each one influences piece cost. And at the end of this section here, when we wrap, we'll focus on a couple of key areas where we believe you can have the greatest control and greatest leverage over the part cost. So starting with paste, one of the first questions we get from customers is, what does Mantle's paste cost? The H13 used to produce this part is $625 per tube, which has 0.8 liters of usable material. So to arrive at how much the paste contributes to this part cost, we take the volume consumed, 614 milliliters, times that rate, and we get $480 in paste cost for this part. Second contribution here, albeit a little smaller, is the labor associated with processing, producing this component here. One of the advantages, and I would say key differentiation between Mantle and traditional machining technologies, other 3D printing technologies used for tool making, is the pretty scarce amount of labor that's used throughout the process. We have automated build setup and tool pathing software that all of our customers have access to. It's super easy to learn, can be learned in minutes, and all of the build instructions are carried out and calculated in the background. So we're able to generate both additive and subtractive tool pathing with no attended time from an operator in a matter of a half hour to a couple of hours, depending on the part's complexity. We've got the time required for an operator to prep the machines, to convey the materials, the parts through the process, all the way through sintering. And our assumption here is that an hour and a half of labor is required. That is attended time at $48 per hour. That's the assumed hourly rate of operators. Contribution for labor is $72 for this part cost, or around 5%. Unpacking consumables here, this is a bit more involved. We wanted to touch on first the utilities required to run both the printer and the furnace. The consumption of the printer on average is about 2 kilowatts while it's running, and likewise with the furnace, 5 kilowatts. So we see the contribution of utilities required to run the equipment there at $16 and $32 for the printer and furnace respectively. We use nitrogen in our furnace to inert the sintering chamber to ensure that our parts come out with the correct tolerances and correct part properties that we're expecting. So we model about $12 of nitrogen consumption per run. And likewise, we take the hazardous waste disposal charges, which customers will incur on average, and this fluctuates depending on municipality, depending on your area. But we're taking a nominal $2,000 assumed rate and dividing it among the assumed number of builds that a customer can run per year. So the contribution here is $12 per part. The last bucket is tangible consumables, so material consumables. That is the support and release material used to cast the substrate on which you build. That is dispensing needles to dose and distribute the paste during the printing process. And likewise, the filters used to scrub particulate and VOCs from inside of the printer envelope. And finally, the cutting tools. Those will have to be replaced on the basis of about monthly. It'll fluctuate depending on the use of each of the tools, but far less frequent than when machining hard tool steels.
One question here, Prescott, is
Go ahead. Sure.
Are those cutting tools, are they custom to the Mantle process, or are those standard, or can you just elaborate a little bit more on the end mills?
Yeah, great question. These are end mills which are available through a variety of traditional vendors. They're not specialty. They are, a distinction here is they are all carbide coated, but otherwise they're run-of-the-mill subtractive tools that you would use on CNC machines, machining centers, and the like. Yeah, good question. The next bucket here is what we would call the contribution of the maintenance and the software subscription that customers have on an annual basis. So that the software package, the subscription, will get you access to Mantle software tool and the capacity to generate these automatic additive and subtractive toolpaths in the background here. And likewise, it also gives you access to the customer service team, customer success team, for maintenance operations, remote troubleshooting, consultation, and so forth. So we take this nominal charge, $25,000 per year, and divide it among the usable hours to arrive at a rate. Apply that rate to the machining time consumed by this part and arrive at $188 for this print. Next category here, as we're rolling up, is that of accessories, installation, and training package. Customers, when they're preparing our site, will have to make some adaptations to accommodate the power, nitrogen, and so forth to set up their facility. Likewise, they have to bring in some accessories and pay for the training and commissioning package. On average, this is around $42,000, which we divide over the full 7-year amortization schedule for the equipment. So taking an assumed rate over that 7-year period and applying it to this part in particular, we get a $50 contribution, or 4%. The last bucket is that of the amortization of the equipment itself. You see these numbers are quite a bit larger. So the way we arrive here is taking the cost of the equipment, both the printer and the furnace, the assumed amortization rate of 7% and utilization of 75, to create a capacity charge, or an hourly cost for operating each of these and occupying each of these pieces of equipment. For the printer, based on our assumptions here, that's around $5.40 per hour. For the furnace, likewise, $3 per hour. So the contributions here for printer and furnace respectively are around $300, or 22% of the all-in costs, and $128 for the furnace amortization.
One question there, Prescott, is
Sure.
that lifetime is not assuming, right, that the system is going to be useless after 7 years,
Right.
or it's a CapEx amortization, correct?
Exactly right. It's a manner of depreciating equipment and leveraging tax benefits. So equipment's by no means useless after that time.
Great.
It'll still continue functioning. Good question.
And hopefully your part costs then are lower, because you can remove this from the equation after that.
That's right. That's right.
Right.
So we're looking at, again, the fully burdened costs. Wanted to wrap this part of the discussion here to show that the paste and the printer amortization are the greatest contributors to the piece cost. And so we would then go on to say that these two elements here, by way of manipulating part design, is going to be the most effective way for someone who's using our equipment to reduce piece cost or influence piece cost, and furthermore the throughput that one's capable of achieving. And through leveraging design, you have a couple of different avenues you can explore. You can reduce the size, that is the overall footprint of a part. You can take some height out of the insert size that you're printing to reduce the aggregate build time. Printing multiple parts together, as it turns out, is a really great way to leverage an economy of scale on the printer, and spread the occupied time in the printer among several parts. And finally, is removing unnecessary features or features that are otherwise easily machinable, which can influence piece cost and throughput to an extent, which we'll explore here in later slides. But I wanted to start here into this component of discussion with another example. This is a pretty sizable part, about 6" by 5" by 2" thick. It takes 144 hours to print in our H13 paste. And having taken it through the same exercise as I just walked through here, the fully burdened cost on this piece is just shy of $3,100. Applying a number of those design conventions, if you will, reducing the height, reducing the spatial footprint of the part, and focusing only on that part detail, which is otherwise pretty hard to machine, eliminating some of the easier, more straightforward features in an injection mold insert, through holes, bores, and so forth. We're able to take that envelope size for the printed volume down to 3.8 inches by 1.8 by a little less than 1 inch. We cut the print time down by about 80%, and likewise the fully burdened cost for this part. So this is a pretty extreme example, but does show you the power of leveraging design to reduce part cost and really increase the throughput you're able to achieve on Mantle printers.
One thing I just want to add here is
Sure.
that a lot of people, they send us things that are on, like what's on the left, and what Mantle is really good at is printing really complex feature details that require sinker EDM, hard milling, etc. We're not great at printing blocks. So as much as you can, focus on printing that feature detail rather than these big blocky shapes that you could mill very, very quickly, obviously you're going to see a lot of value. We also have a question here asking about, does the waste or the cost of the paste include the waste volume of the paste that's machined away, or is that just the paste that ends up in the part?
No, it does. It does. Yeah, it's fully comprehensive. So for the original part, in fact, I'll progress to this slide here. 614 mil encompasses both the final volume of paste that you see there represented in the part, and any scrap material, residual material consumed during the process. Yeah, good question. That'll keep going. So this part should be familiar. It was the original one we used to explore Mantle's cost model. Suppose we wanted to take this part and reduce the part cost. One area you could explore is reducing the XY footprint. And we're able to shave the volume down by a factor of half. So we take the 4 by 3 by 1 down to 3.6 by 2.5 spatially. We bring the print time cost down by 11%. And this likewise has an impact on, the print time down 11%, brings the cost down by 22%. So some pretty significant advantages there. Here's another way we can preserve the volume, but explore what the application of our 4 design rules that we talked about earlier. In this case, we're keeping the XY footprint consistent and diminishing the height on that part. So we're taking it down to 3/4 of an inch. We see the print time cost relative to the print time advantages and savings relative to the original part. We save 19% there, and likewise, the cost associated with this part is 29%. So a 7% difference in terms of cost and an 8% difference in terms of print time. This illustrates a pretty powerful point that we want to make in that we maintain that the height and not parts overall footprint, not the complexity, not the volume that's printed for a given part is the largest contributor to overall print time. And so to expand on that, I wanted to talk about Mantle's process at large for those who aren't familiar. So we have both additive and subtractive operations taking place on the printer. And these operations will alternate. We'll start by dispensing paste through our needle, creating a near net shape. We'll have to then dry that dispensed material to drive off the solvents, provide densification to what we call our green body. That's the part as it exists on the machine, absent its final properties. But that drying process, like I said, it dries the part out, provides for densification, and it also makes the part more robust and tougher. And it permits the use of high-speed cutting tools to shape refine that part. So we'll print a layer on the order of 100 microns thick. We'll dry it, and we'll do shape refinement. And these steps will each repeat consecutively as you build the volume of the part. Pretty simple equation here. You double the part height. Each of these operations will double because you're doubling the amount of layers in the build. So that it's a super powerful dial here where you have the power to reduce the part height. Suppose you have flexibility in the way your mold frame is designed. You could also shim the bottom of the insert up in the mold base to ensure that the parting line's consistent. And the mold frame accommodates a new design to reduce the part height. So this is a pretty powerful lever for influencing piece cost and throughput. The second, and this is related to the printing process, second attribute or second approach one can take is printing multiple parts on a single build plate. We actually see that this is a really good way to improve the effective throughput. And by that, I mean taking the time required to complete a build and dividing it among 2, 3, 4, 6 parts on a build plate. The reason, and I'll expand on this here, the reason we see this as advantageous is because there are some operations that for which the build time increases linearly or proportionally as the number of parts increases, and some that don't, some that are fixed. So the dispensing period, the dispensing time per layer will vary depending on part complexity, paste volume dispensed. But in all, we don't see a huge amount of variance there. Time scales, as I mentioned earlier, proportionally when we have multiple parts on the build plate. Likewise with shape refinement, depending on the feature complexity, detail size, density, and so forth, the cutting time per layer will also be impacted. The more parts you have on the plate, you'll likewise see a proportional increase in the cutting time required. Drying, unlike those other two unit operations, is fixed per layer. So the drying time doesn't vary with part size, complexity, quantity on the plate. We use an infrared lamp that's on a track that will sweep back and forth across the part to drive off, or the full build envelope to drive off the solvent in the dispensed material. For that reason, it's these operations that have a fixed time associated with them, independent of complexity of the part. That's the reason we don't see a linear increase or proportional increase in build time with your part quantity on the plate. So if this trend were linear, we would expect to see a 6x increase in print time with 6 times the number of parts, provided the parts are all the same. We're in reality here because drying time is consistent, and we don't see exactly a linear trend with respect to the other operations, cutting, dispense time. There are big advantages here in the way of packing the build plate with multiple parts. So here's that concept explored, providing hard numbers. On the far left-hand side, we have just one core, or rather one cavity here. Print time takes 42 hours to produce this part. Of that, drying time takes about 14 hours. So we arrive at a piece cost of $889 per part. You double the number of parts on the plate, your print time doesn't double for the reasons I mentioned earlier. It takes only about 60 hours to produce this part, or these two parts, I should say. And the cost per part, given we're spreading both the build time consumed, the drying time across these two parts, and likewise the capacity charge for the printer, we bring the piece cost down to $593. And the build time per part, when we, again, divide it amongst the two parts, down to 30 hours per part. I'm going to go all the way to the right-hand side here. 6 parts on the build plate will take 132 hours. So the build time certainly does compound. It will take longer. But you do see pretty tremendous advantages in the way of print time and piece cost. Around a $500 reduction in the cost per part. And we're cutting the print time per part, the effective throughput, nearly in half when producing 6 parts on the build plate.
This is a good time for a question that's a little off topic, but it actually kind of relates to this part, which is how does Mantle do at printing external threads, which is actually kind of exactly what we're looking at here. These are barb fittings for fluid barb fittings, but that's a question of how do we do at printing external threads?
Yeah, we do a great job. We've had a number of case studies and benchmark parts we've done with partners, provided there are no overhangs on those threads, which, given the nature of our process and the manner in which the paste dispenses and our access to those underhanging surfaces, we aren't able to resolve or shape refine overhanging features. But provided you have the threads laying with the axial dimension in the X or the Y, and the parts laying flat, we do a very, very good job. Molded parts from this sample here that you see didn't have to be refined post-process. The parting line showed up quite well. So I'd say we do a fairly good job. Keep going here with another example. Again, revisiting the original part. So we had seen earlier, this takes 55 hours to print. Merely doubling the number of parts on the plate will take the effective build time per part down from 55 hours to 41. Taking the two concepts we explored earlier, that of reducing the part height and chasing economy of scale here with replicate parts on the build plate or multiple parts on the build plate, we're able to augment those savings even further. So the print time per part's reduced down to 33 and a half hours per part from the original of 55. The third topic here is a statement that I'll make. It's could call a contentious one. Oft-touted in 3D printing, and I've worked in 3D printing now for going on 10 years, 11 years. But folks often make the statement, complexity comes for free with 3D printing. Where in reality, this is simply not true for most 3D printing methods. There are a variety of influences, a variety of trade-offs that one has to be aware of to truly understand what motivates a statement. So I'll try to unpack that here on the next few slides. So we'll use, again, an example of a core component, 2-inch diameter core here. Pretty straightforward. It would be hard to produce traditionally, just given the depth of the features that are cut into the metal. You'd have to use Synchro EDM. In this piece, we're representing it without cooling channels. The total build time is 38 hours and all-in print cost, again, using the model we developed, $839. Um, Suppose you wanted to add conformal cooling to this piece. The statement I'll make is it doesn't come for free, but you'll see it's a very, very marginal increase in both print time and piece cost. So around a 5% change in the print time, up 2 hours from 38 to 40. And the cost per part only increases about 2%. So up from 839 to $856. Again, it doesn't come for free, but the advantages of leveraging 3D printing and the capabilities you have in the way of design flexibility to create conformal cooling, in this example here, could give you tremendous advantages in the way of cycle time and throughput when you're going to mold these parts. So my statement holds true, not for free, but it's a discount you get here. Here's another good example. This part's an amazing part. Great candidate for 3D printing, great candidate for leveraging Mantle to produce this insert. There's a lot of detail on here, which would otherwise need some sync EDM operations to manifest. The part's 4" by 4" by 1.5 inches thick. Print time takes 100 hours, and all-in cost is just under $2,000. So on the next slide, the graphic we wanted to articulate here, illustrate, shows an evolution of part complexity and the impact on both throughput and with both respect to the relative time and the absolute time required to produce this part. What I'm not saying, what Mantle's not claiming, is you should eliminate all complexity from your parts, but understand that there are trade-offs associated when you integrate ejector pin starter holes, conformal cooling channels, simple cooling channels. So to pick on a few examples here, again, we'll ground the data points here, the discussion in the far left graphic, the solid part with minimal tooling detail, if you will, or injection molding detail, takes 100 hours to print. I'll pick on the second from the left, introducing 30 ejector pin holes here on this cavity will cause the build time to slow by 28 hours, 28% slower than the original print time. Integrating additional, or rather taking the solid part and integrating a simple channel into the part detail. Again, as we saw with the original example of that Lego brick core, we see a very, very marginal increase in print time. You don't see a whole lot more a drastic change in print time and throughput impact when going from a more straightforward channel to a more complicated channel. Only about a 9% difference between the two. But this really compounds when you have changes and fluctuations in part detail throughout the Z, complex cooling channels, lots of ejector pin holes throughout the part. So recognizing what attributes of traditional tool making are cheaper, more straightforward to perform. Perhaps it's easier to use a hole popper and wire EDM than it is to produce 30 odd or 40 odd ejector pin holes on a given insert. So you may see that time savings, cost savings associated with integrating or not integrating certain complex features into your inserts when printing with Mantle represent an advantage. So we could just dump all of this information on you, leave it at that, but we want to help. We've got a tool available and consultation that we're willing and able to offer. Again, we'll provide these slides to you via email. You'll be able to use that link to engage with our team and start really trying to understand the impact of Mantle's capabilities, throughput on your tooling production costs.
Awesome. Thanks, yeah. Prescott. As Prescott said, we made this challenging by breaking it out into a bunch of slides that took 20 minutes, but generating that same sort of output is as easy as plugging in a couple of numbers in a spreadsheet. So we're more than happy to do that for you. If you want to go to that link or send us an email, we're happy to do that for your parts. A bunch of questions here, which is great.
Yeah, great.
First one here asking, can we recover a build if there's an issue, a power outage, etc.? What happens then?
Yeah, absolutely. Unlike a lot of other technologies, it's pretty straightforward on the printer to face back. That's the advantage of building your equipment on the backbone of a vertical machining center. We've got a functioning CNC machine that we can use, so it's easy to dock back, machine back, and start your build at a different height. So there's no impact to your build quality, fidelity if there's a power outage or disruption.
Awesome. Another question here about when we're nesting parts on the build plate, can you print dissimilar parts? We showed a lot of examples of the same part being printed multiple
Yep.
times. What if I wanted to print five different core geometries?
Yeah, absolutely. Certainly possible. Number of our customers are doing just that. So yeah, simple answer is yes, absolutely. We'd encourage it.
Yeah, I think our one guideline, right, is if parts are very dissimilar in height, it's not that you can't do it, just that you're losing some of that value of, you could have turned over the whole build or something like
Totally.
that because you're going to be waiting just for one part to be completed.
Yep, exactly.
Um, Question here about, is it possible to put a block of steel into the machine and then print on top of it? Like, put a block of H13 inside of the machine and start with a base already.
Yeah, while it would be possible, I think the challenge comes when sintering. So I'd mentioned part of the drying process, the motivation there is to densify the green body. There's the secondary operation where we stick the part in the furnace, and it will shrink on the order of 8%, 10%, as it further densifies and you get the sintering of the discrete metal particles. Those shrinkage stresses can act to warp any substrate, any metal platen that you have our material printed on.
Right. A question about surface finish. What
Sure.
is the surface finish of a printed mantle insert? What surface finish can we get, etc.?
Yeah, straight out of the machine and post sintering, we're able to achieve a range of between 1 and 4 micron RA. So that's what a D2 surface finish.
Yeah, I think we say it's like a similar to a matte sinker EDM finish.
Yep.
Um, so I don't know how well this probably doesn't come across well in the camera, but this is a part molded right out of an insert that had no finishing done to it. So you sort of get this matte look on it. I'll let Prescott expand on if you needed a better finish than that. What do you do?
Yeah, our parts once sintered are indistinguishable from tool steels. So you can polish stone, laser etch as you would any conventional tool steels.
Right.
So we've had some customers pursue surface finishes as fine as A2, A1, using single point diamond turning. But yeah, it's possible to finish our tools the very same way you would conventional tool steel.
Awesome. Another question about the material. What is the hardness of our material following sintering? Can it be heat treated? Can it be coated with different mold coatings if they want to?
Absolutely. Yeah, out of the sintering furnace, our H13 steel has a hardness of 42 Rockwell. There's a double tempering heat treatment sequence that we recommend customers pursue if they wish to provide additional hardening, and that'll take the hardness up to about 52 Rockwell. We've likewise trialed through partnering with customers different coatings. We've done diamond like carbon, we've done electrolysis nickel. The list goes on. I'm sure, Ethan, there are
Yeah,
a
I think
couple
there's
coming to mind for
Nicholas
you.
Teflon, but I
Yep.
think we tried essentially all of the common mold coatings, and they all were able to be done without any changes to standard operating procedures, which was important. The feedback was they couldn't even tell that the material had been printed, which was really important. A couple of questions here about how do you figure out how much paste your material is going to how much paste your part's going to consume, et cetera. And I'm gonna steal the share here and show something that I spent a lot of time in this week, which is our software and how simple our software makes it to do this. In that you put your part in, you run the analysis. This is just showing the different cutting paths that were generated and all of that. Of course, all that's done automatically. But to answer your question, you can see right here the estimated paste consumptions right here, the estimated print time. Generally, these are about 5% over, which is why we use 55 hours for this part in the presentation. But you can see very clearly right here, this is 614 milliliters of paste. I can then take this number and throw it into my spreadsheet and understand how much the paste is going to cost, et cetera. And then we even have some diagrams here of showing exactly when the paste is used and things like that, as well as what tools are being used throughout the process, when they're being used, etc. So absolutely, you can predict how much paste your part's going to consume before you print it. You can understand how much it's going to cost, which makes quoting incredibly easy, which is some feedback we actually get from our customers is when they're quoting for a customer, it makes it really, really easy for them to understand what it's going to cost for the mantle process, and then what the finishing, the grinding or the finishing of ejector pins, et cetera, will cost. So again, absolutely, you can do all of that very, very simply. And another question here was, because we're doing both additive and subtractive, the paste consumption is not just the volume, right? Because we're overprinting and then milling back. And of course, this software actually accounts for that. And we have some other content that I'll follow up with you actually that actually explains that a little bit more of how much do we overprint by to cut back. But all of that, of course, is accounted for in this 614 number. Another question here. How do we do with finishing of ejector pins? I'll go ahead and stop the share here. Can you answer that, Prescott? Do customers print ejector pins? Do they leave them out? Can you expand on that a little?
Sure. Yeah. I would say the approach most of our customers take is they'll use Mantle to integrate starter holes for ejector pins, ejector blades, and they'll finish them with a wiring operation. Our tolerances that we're capable of out of the box aren't quite tight enough for that line-to-line, that interference fit that you would need with ejector pins. So the additional refinement through a secondary operation to clean those holes up to ensure you get appropriate shut off is necessary. But a lot of customers use our process to integrate starter holes, and they'll finish them.
A question about parting lines. Are parting lines left as printed? Are they warped because of the sintering process? Is there any post-processing needed? I think that's very dependent, application dependent, but Prescott, you want to expand on what you've seen from our customers?
Yeah, of course. I see a variety of different shapes for parting lines, degrees of complexity. I would say for pretty discrete, simple, flat parting line, we're finding that customers just have to dust it on a grinder to ensure you've got appropriate shut off. The flatness the deviation we'll tend to see on those surfaces is on the order of 2 to 5, 2 to 6 microns. So it's in some cases enough that you can overcome it with the sheer tonnage of the press, but you certainly don't have to refine the entire parting line through a secondary operation. I would say that the secondary operations and post-processing isn't nearly as involved as you might think it is.
Yeah, and I would just add to that in that it's very application dependent, where we've seen customers for production of medical device tools where they're touching every surface. We've seen where it's a prototype and all that matters is speed, and a little bit of flash is okay. So they don't touch the parting line, right? Yep. And it's all about what matters to you, whether it's speed or whatnot. And there's certainly you can get it to that if you need to, but a lot of times this is a part I don't think they touch the parting line much, and there's only a little bit of flash here. I think our final question here, and then we'll let you go, Prescott. Thanks again for joining us. Is about tool life. People think of 3D printing a lot of times for prototype tooling. Are these for prototyping? Are they for production? What kind of tool life are we seeing on our inserts?
Yeah, by and large, these are, again, application dependent, but the steels, the resulting properties, hardness, wear resistance that we're able to achieve with our H13 is much alike what you get out of tool steel. So we've got a couple examples of parts running in the field on presses that have seen millions of cycles. So there are customers whose main advantage, the value they're chasing, is the ability to iterate and develop products quickly. Maybe they're only shooting 500, 1,000 shots on each of our tools. But we have a number of examples in the field, like I said, with tens of thousands out to millions of cycles without any need for maintenance or rework.
Yeah, I think this is you've probably seen this part before if you're following Mantle, but this is a Tessie component for a deodorant stick. And I think they're at 1.7 million shots now on 2 different inserts they have of these, and they haven't seen any unexpected signs of wear. So love that idea of, if you need 1,000 parts, great. If you need 1 million, great. It's tool steel. It's durable, which is awesome. Awesome. I don't see any more questions, but great engaging questions, everyone. And thank you very much for giving us 30 minutes out of your day. We're certainly going to follow up with a copy of the slides as well as the recording. If feel free to shoot me an email if you have any questions, thoughts, comments, or click that link. We're happy to take a look at your parts, send us a file. It's really a very easy process for us to run that same analysis for your parts if you want to understand. And we can even give you some feedback of, could you take some height off of this? Could we do this to the part to help you understand how to optimize it for Mantle? I hope everyone has a great rest of your day and enjoy the rest of your week. Thanks.
Thanks, folks.